Welcome to our first video lecture on compiler construction. So today we'll continue to look at an overview of how data flow analysis actually work and how these fit together with the general framework we've introduced in the last lecture. And in upcoming lectures then we'll take a closer look at different data flow analysis that make use of our framework here. So today we're taking a closer look at classical bit vector data flow analysis. So these are called bit vector analysis because information that has to be processed by these analysis can be represented using sets of bits, so vectors of bits. So different elements of a set can be kept in a word consisting of 16, 32, whatever bits. And also all operations we have to perform here can be performed using bit vector operations alone. We need to consider that there are also forms of data flow analysis which require additional operations that are not binary operations, but we won't consider them here. So just to give you a quick overview of how to represent sets in bit vectors here. So we're doing this because we want to have an efficient implementation of sets. So essentially we can keep a number of set elements inside of a simple word. So for example, if we have a 32-bit word, then each bit would just indicate the presence or absence of an element in our set. So if we set it to 1, the element in our set is actually present. If we set it to 0, we would indicate that the element here is actually absent. And so, for example, we can represent the variables in our previous example here as a 5-bit set. So we have 5 variables here, C, D, X, Y, and Z. And so we could assign them to a 5-bit word consisting of bits 0 to 4. So bit 0 would represent variable C, bit 1 would represent variable D, and so on. So with this example here, 1, 0, 1, 1, 0 would mean we have variable C as part of the set, variable D not as part of the set, variable X and Y are again part of the set, and variable Z is not included, so we have a set represented here which consists of the elements C, X, and Y. So if we take a look at our example here, we have all these sets of different variables in our analysis, and now we could simply replace them by just putting the equivalent sets of bits here, which makes it harder to read for us as humans, but which makes it easier actually to operate upon for a computer. Just remember that this is efficient as long as the number of set elements you want to consider here is reasonably small, so usually the number of set elements should actually fit into a simple single machine word. So when we want to do set operations on bit vectors, we can implement the typical set operations on bit vectors using Boolean logic operators that we already know. So for example, we have a union operator of two sets, and this union operator can simply be implemented using the OR operation. So if we have two sets C, X, Y, as we've seen before, represented by 1, 0, 1, 1, 0, and another set X and Z, represented by 0, 0, 1, 0, 1, we can simply do a bitwise OR, so 0 or 1 is 1, or 1 and 1 is also 1. So here we can ensure that each element here, even if it's in both original sets, only shows up once, of course, in the target set. So using this, we can do the union or join operation of these two sets. So we have a joined set of 1, 0, 1, 1, 1, which represents C, X, Y, and Z, which is of course the union of all variables contained in the original input sets. We can also do this for the opposite operation, so the intersection or meet operator of two sets. So we have implemented join as OR, so conversely AND will be implementing the intersection operator. So if we have two sets C, X, Y and C, Y, Z, only using a bitwise AND, only these elements which are present in both sets will have a 1 in the resulting set, so will be parts of the resulting set. So we have C and Y here as common elements, and X and Z are no longer in the resulting set here. If we need a set complement, we can implement it using XOR or a NOT and AND operation, as we'll see in a bit. So we can also use bit vectors to represent the graphs themselves. So bit vectors can represent a graph's adjacency matrix. So what we do is we have our control flow graph here on the left-hand side. We can transform it to a bit simpler representation here, just indicating the numbers of the basic blocks here and the transitions that are possible, so the jumps or control flow edges that are possible between these. And now we can transform this into a set of vectors or a matrix. And so essentially in this matrix we have the basic block we're considering, we have the basic block that is a target of a control flow. And so for example we can go from block 1 to block 5, which would be represented here. So from 1 to 5 we have a 1, which indicates that there is an edge outgoing from 1, incoming to 5, or another edge from 2 to 3 would be going from here to here, would be that one. Now, when we look at control flow graphs, we need to get a couple of definitions right. So if we have an edge in the control flow graph, like that one, or the ones inside here, which we didn't indicate with explicit arrows, but of course we only have control flow in one direction. We can define successors and predecessors of a basic block we're currently looking at. So for example, we have this one here. So the successor of block 2 would be block 3. The predecessor of block 2 would be block 1. Or the predecessors of block 3 would be block 2 and block 5, because there's also an edge going up here. We have two distinguished unique nodes. So we have a start node. This has no predecessor, so we have to figure out the initial conditions. And we have an end node here, which has no successor. So again, for this, we have to define suitable ending conditions. So we do a bit of simplification here. So for general control flow graphs, we might have situations where the end block is not reachable because we have something like an infinite loop. So here we assume that every basic block we have in our control flow graph is actually reachable from our start block. And the other way around, the end block is also reachable from any block inside of our control flow graph. Now, when we want to perform data flow analysis on this representation, we are viewing computation of data through expressions and the transition of data through assignments to variables. So the properties of programs we have explicitly described in our control flow graph are defined now as properties of program entities. So we have expressions, we have variables, we have definitions that make up our program. And again, we take a very simple approach here. So we restrict our expressions to primitive expressions involving a single operator. We've already seen this in 3 address code. So we are splitting up our operations we perform here into simple operations, so we can operate on the intermediate representation we've already introduced. And we are restricting ourselves to simple scalar variables and definitions to assignments to scalar variables. Of course, real programming languages have more and more complex data types, but again, we want to keep things simple here, so we'll keep it to this. So our general approach for performing data flow analysis: if we have something like an expression in a program, our data flow analysis involves 2 steps. So the first step is we want to discover the effect of the individual statements on the expression, and we want to relate these effects across the statements in our program. So very often we've already seen that we don't do this on a single statement basis, but for reasons of efficiency, both steps are usually carried over a basic block instead of a single statement, because then we have less blocks to care about. There are actually approaches that consider going back to single statements again, because the original concatenation of instructions into basic blocks was mostly used for efficiency. Computers might now be fast enough. There's an interesting PhD thesis on this, but we'll consider basic blocks again because that's what's common in literature so far. So we have 2 steps: the discovery of the effect of individual statements on the expression. This is called a local data flow analysis, and this is performed once for every basic block. And we have the relation of the effects across statements in the program. And as we've already seen in our introductory example in the lecture 2 lectures ago, This is our global data flow analysis, and this may require repeated traversals over basic blocks in the control flow graph until we reach a fixed point, so we figure out no more changes are going to happen. Take care, global here means we're not looking at the complete program, but we're only looking at the effects of data flow inside of a single procedure, so we're not assuming that effects currently traverse beyond procedure bounds. So we start with something inside of procedure, we end with something, we have incoming, outgoing data inside a procedure, but that's also global. Might be a bit misleading, but that's what's used in literature again. So when we want to discover local data flow information, it depends actually on the analysis we want to perform, how we are going to model this. And we're going to have a closer look at this in the upcoming lectures. Nevertheless, there's a common pattern of data generation, data flow generation, and or invalidation, of course, of data flow information. So we have these elements here. So for the entities we have in our simple intermediate representation, so variables, x, so scalar variables, expressions, and a definition of a variable. So we assign something, an expression, the result of an expression, to a new variable here. We can have two operations each. So for variables, we can read a variable, our x, so we use it, or we can modify its value. For an expression e, we can compute it, or we can modify an operand of the expression. And for a definition, this might occur, or anytime we have an x, this might happen here. All right, so a variable may be used, or an expression may be computed. On the one hand, in the right-hand side of an assignment statement, then in a condition that alters control flow, so a loop or an if condition or a case statement, or as an actual parameter in a function call, or as a return value from a function. All other operations, so not using variables or computing expressions, involve an assignment statement to a relevant variable here. So you might be asking yourself, what happens if we're reading a variable from input? So we've seen we can't really predict what's happening then. So we can safely consider this as an assignment statement that just assigns an unknown variable a value, so question mark or something we can use to represent this, to the variable. So we don't know a lot about this then. So when we look at local and global data flow information in our control flow graph, we need to capture this relationship between local and global data flow information, and we capture this using so-called data flow equations. And data flow equations are in general a system of linear simultaneous equations. We have to solve these, and you know this probably from your linear algebra. So in general, these equations may have multiple solutions. So how can we actually consider data flow equations, and how can we obtain these? So in forward flow analysis, we have interesting things. So we have the exit state of a basic block B, we call out B, and this is a function of what's happening inside of our basic block, like this assignment here. So out B is trans B of in B, so essentially trans B is the transition function depending on the code contained in our block. And since we have multiple instructions in general in a basic block, this is actually the composition of all the effects of all the statements in the block. So we look at what's coming in, we apply all the operations inside of our block to our input variables, and then calculate what's going to happen with the output variables. Now, this is simple as soon as we have a single basic block. Now, what happens if we have some join of control flow? Then we have to consider both paths or any path we are arriving on. So for example, we have a path going via B1 and another path going via B2, and they join here in block 3. So as the input sets of this block B3, now we have to consider the join of both information sets coming in from B1 and B2. So the entry state of a basic block in general is another data flow equation, a function of the exit states of all predecessors. So in B is the join of all predecessors of our current block we're looking at. And of course, we join their output values. Of course, for a single block like this one, this is simple because we only have a single block coming in, so we don't have to join anything. And if we have joint control flow, we have to consider all of these. So these combine the exit states of all the predecessors, and this is then the combined entry state for our block B we're currently looking at. So in this case, this would be the block B3. So we can perform data flow analysis in two directions, and each type of data flow analysis then has a special transfer function and a specific join operation applied to them. And so we can do forward analysis like this. So in a forward analysis, we traverse the control flow graph along the direction of control flow. So this can be used in several analyses like reaching definitions and available expressions we're going to look at. And we can do it the other way around. So we can do backward analysis. So we can look from the output to the input and see what happens there. So we traverse the control flow graph against the direction of control flow. This is used, for example, in live variables analysis or something we call very busy expressions analysis. So here we apply the transfer function to the exit state and we yield the entry state of this block. So the join operation now works on the entry states of the successors to yield the exit state. So it's just doing it the other way around, and depending on which analysis we're going to perform, we need one way or the other. So when we're doing bit vector analysis, we can consider two special sets, so-called gen and kill sets. So we have already seen bit vector data flow analysis works on sets of facts. So facts are just the information you care about, and these sets can be represented efficiently as bit vectors, and we've also seen join and transfer functions can be implemented as logical bitwise operations. So join can be the typical intersection or the combination operation, so we implement them using a logical or a logical and the transfer functions, and that's important because that makes bit vector analysis quite a bit easier than other analysis, can be decomposed into two sets, and these sets we call the gen and the kill sets. So gen describes the points in the graph where a fact you care about becomes true. So gen of a block B describes data flow information that is generated within a basic block B. And kill, on the other hand, describes the points in the graph where a fact that you care about becomes false. So kill B describes data flow information which becomes invalid, contrasted to generated in block B. And so we've seen we cannot have just a very general abstract definition because we need to specify the gen and kill points and sets depending on the facts that we care about, so depending on the analysis we're actually going to perform. So we have an example for gen and kill sets here. One example is live variable analysis. For this, our join operation is union. So our kill sets, we want to see which variables are live, are the variables that are written within a block. The gen set are the variables that are read without being written first. And so the related data flow equations are out B is the join of all the input information about all these successors. So we're going backward here. And in B is then, we're looking at the out B first. We're removing the kill B elements that are killed in the current basic block we're looking at. And we join them with the ones that are actually generated in the current basic block. Now this is always expressed in form of set operations. So if we want to implement this actually, we can do this using logical operations using this piece of code. So we start off with an empty set for out of B, and then we populate out of B by looking at all the successors of B here. And so we add the input sets of each successor to the output set of B here. And when we traverse through all the successors of B, we can finally construct our input set, which is the output set that we just considered. And from this, we remove using the AND NOT operation. So we invert our kill set here. So the ones which are killed, we want to remove from out. And then we join this together using the OR operation with the ones that are generated in B. So that's all for today. We have some references here. There are some interesting books just covering data flow analysis alone. As you've already probably imagined, this is a quite complex topic and we're only scraping at the surface here. So data flow analysis have actually started very early with Gary Kildall, who already unfortunately passed away several years ago. So he's actually famous for developing the first common personal computer operating system, CPM, for 8-bit computers, but he did his PhD thesis actually in 1973 on data flow analysis, and he was the first one actually to perform global program optimization. So he was thinking of translating code between processors of different instruction sets. So he was writing a converter from 8080, Intel 8080, the first 8-bit processor by Intel, to 8086 code, because both operating systems or both processors were supported by a CP/M operating system. And he actually built a translator that was able to transfer code on assembly source code level from 8080 to 8086, and he performed some optimizations, and these were the result of actually his analysis on this. So he used a very practical problem to derive a very interesting theoretical approach, and this paper is actually interesting to read. So, as I already announced, these lectures are going to be a bit shorter than our regular lectures, and we have a couple more of these. So essentially, upcoming lectures then will look at several different examples of forward and backward data flow analysis. But that's all for now. So thanks for listening, and see you next time. Bye.